Alright, so let's prove some other properties of isomorphisms. Let phi from G to H be an isomorphism. Then one of the facts that the book says is obvious is that the inverse function is also an isomorphism. I'll actually prove that because one thing that's not obvious is that preserves products. The fact that it's a bijection is obvious. 2, assuming G is finite, these two have the same size. That's clear just because of the fact that being an isomorphism means you're a bijection. 3, G is abelian if and only if H is abelian. The textbook only proves one direction, but if you apply this property 1, you get the reverse direction. The book has that proof, so I'm not going to do it. I'm going to focus on 4 and 5, which the textbook does not prove. 4, G is cyclic if and only if H is cyclic. And 5, if G has a subgroup of order n, then H has a subgroup of order n. So let's prove 1. Phi inverse is a bijection. So I only need to prove the multiplicative part. Let x and y be in H. Well, by definition of the fact that phi is an isomorphism, then we know x and y are equal to phi of A and phi of B for some A and B in the domain group G. Why? Because phi is surjective. So what's phi inverse of x times y? Well, because what do I want to show? I want to show phi inverse of x times y is equal to phi inverse x times phi inverse y. And I don't have much room to work with. The only thing I can really work with is by replacing x and y with elements in G and with phi, because I know stuff about phi already, and so that's what I'm doing. So I can replace x and y with phi of A and phi of B. Then I could take advantage of the fact that phi preserves products to replace phi of A and phi of B with phi times A and B. Then I can use the fact that phi inverse is the inverse of phi. So phi inverse of phi is the identity map. So this expression is just A times B. But what is A is phi inverse of x. What is B? It's phi inverse of y. So we do actually get that phi inverse preserves products. And since it's also a bijection, it is therefore an isomorphism. Alright, now let's look at 4. Suppose G is cyclic. Well, suppose it has order n. And then suppose it has an element G of order n. Then in the previous video, we proved that phi of G also has order n. By property 2, the two groups have the same size. So H has an element, namely phi of G, of order the size of the group. That means H is cyclic. Likewise, by property 1, phi inverse is an isomorphism. So this first paragraph shows that if G is cyclic, then H is cyclic. The second one says that you have an isomorphism in the reverse direction, so if H is cyclic, by this same argument applied to H, G must be cyclic. So notice 4 is a different property than what we proved last time. Last time we proved that if G and H were two cyclic groups of the same order, they have to be isomorphic. This part shows that if G and H are isomorphic and one of them is cyclic, then the other one has to be. In particular, if one of your groups is cyclic and the other is not, then there's no way they can be isomorphic. Just like if one of your groups is abelian and the other is not, there's no way they can be isomorphic. So the last claim, if G has a subgroup of order n, then H has a subgroup of order n. Let me actually just state it the way it ought to be stated. A more precise statement is given a subgroup of G, K is isomorphic to phi of K, where phi of K is the image under this isomorphism. Or equivalently, if you've got a subgroup of H, then you better get the inverse of K is isomorphic to K. But that follows from the fact that phi inverse is also an isomorphism. So what do I need to check? I need to check that phi of k is in fact a subgroup, is in fact a group, and that there is this isomorphism. The easiest way to see this fact is to define a new map called phi restricted to k. It's a function from k to phi of k, defined by the same formula as phi. So the only difference is you're only allowed inputs from k. And so we've restricted the domain and we've restricted the codomain. So it's not all of H, it's just the elements in H that were actually in the image of K under phi. And so it's not too hard to show that phi restricted to K is still a bijection. Namely, take an element in this codomain, y. You need to find x that maps to it in order to show that it's surjective. Well, this codomain is an image set, so by definition of image, there exists an x in K such that phi of x equals y. We define phi restricted to K by the same formula, so phi restricted to K of x is also y. Congratulations, we found an x that maps to y, therefore phi restricted to K is surjective. Likewise, suppose phi restricted to K of x is equal to phi restricted to K of x prime. We want to show x is equal to x prime so that we can conclude that the restriction of phi to k is in fact injective. Well, phi of x is equal to phi restricted to k of x. And phi restricted to k of x prime is equal to phi of x prime. So we see that phi of x is equal to phi of x prime. Since phi is assumed to be injective, it follows that x is equal to x prime, because now we have phi of x is equal to phi of x prime. And so we see phi restricted to k is a bijection. Finally, if we take two elements in k, x and x prime, and we do this calculation, this product, well, by definition, phi restricted to k of x and phi restricted to k of x prime is equal to phi of x and phi of x prime. Since phi preserves products, phi of x times phi of x prime is phi of x times x prime. One would like to say that's actually equal to phi restricted to k of x prime. And then you could say this map preserves products. There's just one little gap here. This step right here is assuming that x times x prime is an element in k. But we're okay there because k was assumed to be a subgroup of the domain. So phi is a homomorphism. So if phi of k is a subgroup, of H, then we do in fact have that k is isomorphic to phi of k as groups. So why should phi of k be a subgroup? Well, here I'm going to use the fact we actually have a bijection for once. To make this proof a little easier, we're going to prove a generalization of this result later in the course. But we have two elements, x and y, in phi of k. By the subgroup criterion, we're going to want x, y inverse in phi of k. So what I'm going to do is, since x and y are elements in the image, it follows that phi inverse of x and phi inverse of y are elements in k. Here I'm using the fact that phi is a bijection, and so phi inverse is a function that exists. So this is something you normally can't do, but in our case, you are allowed to do this. So we're going to take advantage of that because it makes the proof a lot easier. I'm going to multiply phi inverse of x times the inverse of phi inverse of y. Remember, we proved that phi inverse is also an isomorphism. So by properties of isomorphisms, the inverse of phi inverse of y is phi inverse of y inverse. And the isomorphism preserves product, so I get phi inverse of x times y inverse. So what do we get? We get that this last element, the inverse of this product, is equal to this product of inverse functions. That's what we started with. These were elements in K, so this weird calculation is also an element in K since it's a subgroup of G. Therefore, phi inverse of this product is also in K. So now if we compose this element with phi, we get an element in the image. Phi composed with phi inverse cancels, so we now find out that xy inverse is in fact in the image. This is a complicated trick to use the inverse function and properties of bijections. There's an alternative argument we'll see in a later video. But this is an alternative approach that can be used specifically because we have a bijection. So this starts to lay out a stronger fact. If you let S of G be the set of subgroups of a given group, then when G and H are isomorphic, then the collection of subgroups are in bijection with each other. Because each subgroup is isomorphic of G is isomorphic to a subgroup of H. And literally it's a one-to-one correspondence. They correspond uniquely, which is kind of cool. That's a stronger result. That takes a little more work, so we haven't actually shown that yet. But the corollary from what we just showed is that, of course, K has the same order as phi of K. So if G has a group of order n, then so does H.